Hello and welcome to flight controls for the Airbus A350. Going to give you an overview, just a quick overview of the entire flight controls topic, and then I'll go ahead and delve into session 1. Alright, the different sessions that we have for this topic is number 1, session 1 is the behavior of the airplane. What can it do and not do? It's important to understand what those are and limits, etc. for the safe flying of the airplane. And I'm specifically obviously talking about commercial passenger and cargo airplane. Session 2 is control modes, or maybe you've heard them as laws or limits. Basically it just has to do with the limits of aerodynamics. And session number 3 is the flight control and performance devices. This is the how, how do we control the plane flying? We do it with the flight control devices, and also I'll describe later about the primary, the secondary, and just identify what those are and give a general description. Session 4 are your actuators. We're going to delve into the different kinds of actuators that are used on the aircraft as it pertains to the control devices, or the flight control devices. Session number 5 is the primary flight control system. Session 6, slat control system, and our session 7 is flap control system, and our last session is session 8, and that's your THS control system. Ground spoilers, I'll throw that in also, so ground spoilers as well as speed brakes. Your THS is your trimmable horizontal stabilizer control system. Alright, so that gives you a quick, again, that's just a quick overview of the different subtopics that make up the flight controls topic. And at this point, what I want to do is introduce you to, without giving detailed mathematical lectures or conceptual, lectures about the relationships involved with the parameters in aerodynamics. I just want to give you a general understanding of those different parameters. All right, so this is again just a foundation of understanding the commercial type jet aircraft, because fighter jets is a whole different ballgame when it comes to aerodynamic design and what its capabilities are in flight, and safe flight. But we're talking about commercial passenger and cargo aircraft here, so obviously it has a whole set of rules of what it can and cannot do, and we're going to identify that. And so let's go ahead and just start with 3 positions of the airplane. As it's flying, it's going, we have a horizontal situation. Okay, so basically the plane can go nose up or nose down. That's one position. Okay, either nose up or nose down. That's what's called pitch. And then you also have roll, which the plane can go right or left along an imaginary line that goes longitudinally. So that's your roll, is to the right or left. And then of course your yaw is a moving to the right or to the left without dipping the nose. It just moves laterally, right or left. So those are your 3 positions of the airplane. And when it's in flight, obviously there's maneuvers that are going on because the pilot is giving inputs so that the plane can maintain a certain flight path and maintain a certain heading and direction based on destination, right? And in order to do all of that, there are different parameters that are involved to make that happen. Number 1 is rotation and derotation. Your rotation has to do with actually takeoff. So not in flight, but the plane is actually getting, revving up the engines and gaining that speed and actually taking off on the runway. The challenge here is to have the right amount of pitch, angle of attack, and a certain rotation so that when it does take off nose up, it doesn't hit, the back of the plane doesn't hit ground. Okay, so you don't have a tail strike on the ground. That's number 1. Number 2 is an angle of attack, okay, which is a protection against stalling the plane. Number 3 is a bank angle. And that's protection also against stalling the plane, okay, or a fast descent, which can happen with a bank angle. And I'll explain a little bit more what's involved with these different aspects or parameters. But you also have high speed. you know, that's a generic term. You think, well, high speed, what is that? Because, you know, how many knots? But high speed, we're talking about protection against too much compressibility of air that happens when the plane is going at high speed. And just for the record, your commercial aircraft are going at speeds just below Mach 1. Okay, that's just, which is the speed of sound. So your range is about 0.7 to 0.9 of Mach. Again, right before that. But what's happening is it's pushing the air, and so you have a compressibility of air, which causes the density to change, and then you have these shock waves that occur, and that's going to be affecting the drag and the lift of the aircraft. The next thing you have is load factor. And what is load factor? Load factor is a protection against critical stress. When we talk about protection, when we look at load factor, we want to make sure that it's within a certain range. It's because we don't want to have stress on the structure of the aircraft. So load factor is kind of an apparent, or kind of a feeling of a certain acceleration of the aircraft. The next thing is your rudder deflection. If you have it go too far, like you can have it at max range, but if it does exceed a certain deflection, then you're going to have a different situation, what's called a rudder hardover, and that definitely is going to affect the structure of the plane, and you know, it's going to be disastrous. So that's what you have with the rudder deflection. And then a last aspect to this whole operating the plane and controlling it is turbulence damping. Obviously there's turbulence in the air at different altitudes, at 40,000 feet, at 5,000 feet, you know, depending on how the turbulence is, the weather and all kinds of atmospheric conditions that make it conducive for a turbulence condition to exist. And it's not just damping the turbulence for the air, you know, the passengers to not, you know, feel like, oh my gosh, we're taking a big dive here. But it's also a threat to the wingtips. So we have an issue with structure threat with turbulence. Okay, so let's start with the first one. I mentioned rotation and derotation. The pilot has the responsibility to have enough back pressure to the manual inputs so that it can get that nose wheel up and off, those wheels off the ground, so it can take off, right? Basically, you're manipulating it, you know, kind of a fine balance with the right amount of speed, the pitch, your angle of attack, in order to safely clear the tail of the plane from the ground. So, and there's been incidences and accidents, okay, there's incidents and accidents, where the pilot input was not quite right and there was a tail strike. So, that does, or has happened. Okay, number two, you remember angle of attack. Your angle, okay, what's the angle of attack? Okay, let me define it. Your angle of attack is the angle between the chord of an airfoil. Kind of gives you a reference line, and then the direction of the surrounding flow of air. So that's the angle that's there. And again, we know if you really wanted to get into aerodynamics, we could really get into detail on theta and beta and all these different angles that are defined when we talk about aerodynamics and relative wind and the airflow that's around the various parts or components of the aircraft. Number three, your high speed protection. What's high speed? Okay, what's the danger to be concerned about when we talk about high speed, you know, the plane running at a high speed? Well, we're talking about what happens when the airplane is pushing through the air and at a high speed. Okay, when I talk about high speed, just somewhere, it could be just right below Mach, or it could be even lower than that. But we're talking about enough of a speed that compresses the air around the aircraft. And the danger with that is it changes the density as a result. And then it also creates these shock waves. And all of that can affect the lift of that airplane, okay, and also the drag. So just kind of some terms that are used that you might see in manuals at your MRO or whatever, or your VMO and MMO. Okay, that has to do with speed. V stands actually for velocity, but you know, velocity is speed and direction. Speed's just, you know, in one direction, but your maximum operating speed, okay, so there's two different units of measure. When you see VMO or MMO, they're the same idea, but they're two different units of measure. So when we talk about VMO, that stands for, that's maximum your operation speed in knots calibrated airspeed. And that's usually used for lower altitudes when they use the VMO as a measure. Your MMO has to do with Mach. Okay, so that's what that Mach is maximum operating speed, but in terms of Mach numbers. And those are usually at higher altitudes, because that's when you're, you know, ending, or your potential for getting closer to the speed of sound is much greater. Okay, so what are your threats for exceeding these limits? If for some reason, you know, if the aircraft is pushing through the air, it's going at high speed, and it's pushing to maybe Mach 1, let's say goes up to, and maybe includes Mach 1, you're hitting a different realm that could easily go past that, which is a transonic. There's different kinds of, or levels of speed, and this in particular, we're concerned about a transonic condition, and that becomes a structural damage, can cause structural damage to the plane when you have the exceedance of these maximum operating speeds. That includes the fuselage. You may have heard already of airplanes which have had that happen, where, you know, there was a threat to the structure, you know, for whatever reason, you know, whatever the cause was. If you have a structural threat, it's a chain reaction. You know, the rudder starts to break apart, then now you've just, you know, you've threatened the integrity of the entire structure of the aircraft, and that's when, you know, it's a domino effect. Other components to the aircraft can begin to break apart. Also, you have a slower aircraft control response due to the compressibility effects. So that's another result of exceeding these limits. You also have loss of lift. Remember I said that it affects lift and drag. You'll have increased drag, but your lift is actually going to be decreased. And that's because you're not having that airflow to use around the aircraft. It gets kind of, there's more of a gap between that airflow and the aircraft as it's pushing through at beyond the limits of airspeed. And again, that shock wave is created, so it kind of creates this separation that the aircraft doesn't have the leverage, if you will, to continue to have a certain lift that's necessary. Remember I said drag, that's just, it increases the drag. So it's just much more difficult at that point for the aircraft to actually stay, you know, lifted up in the air. Your vibration and buffet, that's also another threat, vibration to the aircraft. Some of the terms that you may or may not be familiar with as it results or has to do with all of this is aileron reversal. Some pilots have actually utilized the aileron to offset some of that because they are trying to gain more lift. There's also a thing called the Mach tuck and also the buzz. This has to do with Mach buffet, when the say Mach buffets. And these are just, again, having to do with the problems that arise from exceeding limits when the plane is at high speed. The next thing is load factor. A load factor is basically it's a ratio of the lift of the aircraft to the weight of the aircraft. It's just like a feeling of the load on the aircraft, but it is a measure of the stress that's put on the aircraft. Okay, it is measured in G's, so if you see a range, you know, of -5G or whatever, number one, you're seeing a range, then that's what the G stands for. It has to do with the gravity, even though it's not, you know, we're really not talking about acceleration, but it's just the sensation or the feeling of acceleration of the gravity that's, you know, that you're feeling on board, and that's what that is. And of course, that's when, you know, when pilots are needing to maneuver, for example, much more when they're maybe going through turbulence or doing a banking, you know, the turning. So you have those. Also, if there's a gust of wind, that'll also be felt as well. All right, what about your rudder deflection? Very important with rudder deflection. There's max ranges, obviously. You can talk about, you know, if you worked on the airplanes before, maybe you worked with the rudder limiters. I talk about that with the DC-9. The limiters are, you know, there to protect the rudder from, you know, exceeding its range, you know, its mechanical range. But, you know, should we really rely on that? You know, I mean, they're there, it's good. But, you know, the pilot can actually push the limit. You know, he could push beyond if he wanted to. And I know in some cases, for example, there's American Airlines Flight 585, and there's a U.S. Air Flight, I think it's 427, and also East Wind Airlines from the past, Flight 517, that had rudder deflection exceedances. And one of them, actually, two of them were fatal. One of them was not, because the pilots were actually using the rudder deflection to try to regain control of the craft. It kept, they went it's like doing a hard right. It's like you're driving and, you know, your car is pulling to the left, and you want to do a hard right so that you can, you know, overcompensate. So somehow you're going to be centered after doing that, right? But the thing is with this aircraft, I think it was the American Airlines one, that it kept pulling even after the pilots were trying to get it. It seemed like they had some success to get it sort of under control, but then the plane still, you know, wanted to do its own thing, as I call it, like the poltergeist. Like, it's kind of just on it, has a mind of its own, and it kept pulling that way. But it was defective, it turned out. There was some problem with the power control unit, actually, on that particular instance. But, so that's rudder deflection. You want to make sure we have protection, you know, with the components functioning properly, that we want to make sure that the rudder deflection command orders are, you know, are obviously translated into the rudder actually doing that. So that's pretty important if you have damage to the rudder. Your last one here, last one is turbulence damping. Turbulence damping is important for two reasons. Number one, you don't want to have undue stress on the wing tips, because what's on the outer, you know, what's on the outer, you know, outer part of the plane? Well, the wings, and of course further out is the wing tips. And when there's turbulence, you know, they can be subjected to quite a bit of strain from wind, you know, gusts and whatnot, and just that turbulence that occurs at any particular band of altitude in the atmosphere. So it's important to have a damping system. The other thing too, if the pilots are going through a turbulence and they're manipulating the maneuvers to kind of, you know, ease that experience, some of the damping systems that exist they're there to help everybody on board to give a sensation that it's not a 9-foot drop, it feels like a 3-foot drop. So it's, you know, again, it's just balancing it out. And incidentally, the Boeing 787, which is also known as the Dreamliner, has added the accelerators to the nose of the plane for that very reason. Okay, so, you know, some have it, some don't, but that's the reason why they're there. They're trying to, you know, send commands, you know, after getting the sensors of, okay, we're now experiencing a very sudden drop, but then in nanoseconds, boom, it sends out that information through computers to change the wing flaps so that it can just very, very fast to offset, you know, that feel. So it's pretty neat that those damping systems exist on some aircraft. Okay, so it gives you an idea. Certainly these are things I wanted to make sure that I brought these terms up to you and that I explained as much as I could without getting into a whole aerodynamics lecture for a semester or two. And just a basic understanding of what rotation, you know, derotation means. I know it's the manipulation, so we don't have a tail strike, your angle of attack, bank angle, things like that are affecting the lift of the aircraft. Okay, so lift and drag are extremely important, and having these conditions of angles and mixed with speed affect it. So that's what you have with all these terms. our next session. So hopefully this is preparing you for session 2, because session 2 I'm going to talk about control modes and what on the aircraft as far as the components or systems are going to be in charge of certain flight control devices to make sure that the plane is, within certain limits, these, for these parameters that I just mentioned. All right. Okay, so that covers session 1. We're going to go ahead and go into session 2. Welcome to the next session. This is session 2 on flight controls for the Airbus A350. Session 2 is entitled Flight Control Laws. In our first session, we did cover the different aspects to the airplane as far as its behavior in flight and some of the limitations that the plane has. When we talk about flight control laws, and incidentally, the word laws is pertaining to Airbus in particular. The Boeing 777 refers to it as modes, and some other aircraft manufacturers may refer to the flight control conditions as either laws or modes, but Airbus specifically uses the word laws. So what do we mean by laws? Okay, we're talking about computers on board the aircraft that are going to give command orders based on sensor inputs. Okay, whether it's coming through from the pilot or from the Ailerons or some other source, where it's going to be able to just determine what those limitations will be in actuating the surface devices, the control surface devices. So here in this particular case, there's normal, alternate, direct, and abnormal law. And be aware that this is specifically Airbus. When we get to Boeing 777, the terminology may be slightly different regarding the modes of protection in the different phases of flight. Here on Airbus, there are the 4 different ones: normal law, alternate law, direct law, and abnormal law. The first one, normal law, that means when there's that normal law, meaning that again, primary or secondary computers are receiving inputs and giving commands. This is going to be for protecting the aircraft in all the different kinds of ways, as we talked about before in session 1. Some examples that I'll just refresh your memory on: rotation law. Okay, we want to avoid tail strike at takeoff. Number 2, we're talking about also maybe the load factor protection. Load factor, if you recall, has to do with the sensation or feeling of the, push or whatever on the aircraft at certain speeds, and just that acceleration factor. Angle of attack also, and your comfort law. This has to do with your turbulence and the aircraft computers trying to lessen that feeling of the turbulence. But these are just some of those things. So when normal law, just know that the aircraft is protecting, the computers are protecting the aircraft from too much speed, high speed problems, your pitch, basically protecting it from stalling, etc. Now, in alternate law, alternate law means you're going to have a failure of at least, I would say, the 2 computers. That could vary a little bit. So just know that there's a failure of something. Typically, it's going to be both computers. When you look at the laws in alternate law, there could be some variation as to how it's defining what that alternate law is, depending on whether or not there's one sensor that's failing or you have more than one. Okay, so just keep that in mind. It's not a hard and fast rule, but it just do know for the test purpose that normal law is complete protection. Alternate law is not complete protection. It just allows for some protection. And number 3, your direct law, there is no protection coming from any of the computers. These are going to be complete failures. You could have failure of the hydraulic system as well besides your computers. Direct law is just direct input straight coming from the pilot. And then your abnormal law, this is the law where the system is trying to offset any collision or consequences of a collision or extreme weather conditions or atmospheric conditions. All right, so those are your 1, 2, 3, 4. Those are your 4 different flight control laws, and the computers that are there to, again, read those inputs and determine then what the command is going to the actuators of the control surfaces. And again, this is the whole objective with all of this. All these different computer systems obviously is to ensure that the plane is maintained in a safety condition at all phases of flight. Okay, and just so you know, on the kind of the split of what what's in control of what, your primary computers are the ones that are going to be operating or running the normal, alternate, abnormal laws, and direct laws. Those are all operated in the primaries. Again, if you have failure of the computers, obviously there's not going to be controlling any commands, but if they are functioning, then they will be able to to operate in those. And then your direct and abnormal law is in the your secondary computers. That's mostly for your secondary flight control surface devices, like your spoilers. Okay, and then you have also your specific direct law, and that's in the backup control module. Okay, they're programs. Okay, so that gives you an idea with that, and that the whole idea here is just different levels of protection for the aircraft in different phases of flight. And just keep in mind that it's a degradation. What I just said right now, in the order that I presented them, the normal law, alternate law, direct law, and abnormal law, the order that I just presented it is the order of the highest level of protection to the lowest, meaning, or pretty much the lowest, where there's no protection. For example, in direct law, there's no protection. So kind of keep that in mind for test purposes as well, but just in general, keep that in mind. Okay. Direct law, you have absolutely no protection. Okay, and we'll get into more detail in the on the computers, but only as I'm talking about, for example, the primary flight control system. I'll specifically talk about the computers pertaining to that. Or when we talk about the slat and flap system, or I'll introduce the CFCC. Those are your slat flap control computers. This concludes our session 2 on the flight control laws for the Airbus A350. Welcome to session 3 on flight controls for the A350. Session 3 is on the control surfaces, so I'm going to talk about, describe, identify the different control surfaces that are on the Airbus A350 and all airplanes for that matter, and also go into a little bit on the computers and just mention some of the actuators that are associated with these control surfaces. We will talk in more detail on the session on actuators as far as description and what's all involved. For now, let's just go into the control surfaces. With here we have, you can break this up into 2 different types. You don't have to, but it's just a way to compartmentalize the information. You have primary flight control surface devices. You also have your secondary. And what differentiates those 2? Basically, what you have with primary flight controls is they are essential with keeping the plane in the attitude that it needs to be, basically flying the plane. The secondary flight controls are there to fine-tune the performance of the attitude of the airplane. Okay, and what we have on the primary flight controls is your ailerons, elevators, and your rudder. Sometimes we can add a little extra with that depending on how we use the spoilers, but at any rate, the ailerons. With the ailerons, this helps keep the plane in balance when it comes to the rolling of the plane. So that means rolling, left to right. It helps with balancing that out. The ailerons are located on the airplane on the trailing edge of the wings. Okay, and again, those are just to balance out laterally from left to right. It also creates a condition of tilting of the lift vector. So this has a lot to do with the lift. Number two, you have elevators. Your elevators have to do with helping with pitching the airplane. Okay, that's nose up, nose down. These are located on the horizontal stabilizer at the rear of the plane. And again, that's controlling the pitch of the airplane, which is going to affect the angle of attack and also the lift of the wings. Number three is going to be your rudder. The rudder is affecting the yaw. Okay, and that's kind of like the pulling laterally from right to left. So that's different from the rolling, which dips downward to the right or left. The yaw is keeping, at the same axis, moving right to left. And this is controlling the surface, controlling adverse yaw, so keeping the plane more centered. And also the P factor is also not the primary control used to turn the plane, but again, it's just helping with the yaw, so there's not an imbalance there. What it's doing when the rudder is actually moving, it's changing the airflow, as many of these control devices are doing. It's what all of them are doing, actually. But depending on where they're positioned or located on the plane, it's going to have a different effect. And here it's doing the same thing with redirecting the air passing the fuselage. Okay, those are your basic. Just think of AER. Okay, that's your ailerons, your elevators, and your rudder. AER, air, comprise your primary flight controls. Now, there's some also what can be considered part of primary, helping a little bit, is your spoilers, which your spoilers are there to help with obviously spoiling the flight of the aircraft. So it's going to create some drag, but it has a couple of different functions. One, they can be function as ground spoilers, and that has to do with coming in for a landing. And then you have some spoilers as you're in flight, just in flying to, again, depending on the condition at any given altitude in the air. Your flaps, your flaps and slats are going to be primarily your secondary flight controls, and flaps, for example, are going to be affecting the lift. It's sort of a high lift device, and its job is to increase the lift of the wing at a certain airspeed. When they're actually extended, and you can notice them if you've been around airplanes, you know what I'm saying, but when they're extended, they're increasing the surface, right, of the wing. And when you're doing that, it's also creating a more of an aerodynamic design. So when it's doing that, it's creating a curvature, which of course is increasing that surface area as well and creating lift. What it's as a result of doing is reducing the stalling speed. So again, it's helping when you have you need extra lift pretty quickly, which would be at takeoff and also in descending, because at that point when your speed decreases, and you want to actually have some lift at that point, because you don't have the power behind that when you have reduced speed. So that's what's going on with the flaps and why they're there. They are located on the trailing edge of the wings. Now, what about the slats? They're very similar when we think about flaps and slats. But slats are located, just so you know, they're not on the trailing edge. They're on the leading edge of the wings. They're also kind of a high lift device and creating an aerodynamic surface there on the leading edge. They're also reducing the stall speed. They're retracted normally so that they're not, creating a drag. Obviously, they're deployed, they're creating a drag by doing that. So why are they there? We have the flaps on the trailing edge, and then we have slats on the leading edge. And we have a similar situation where it's allowing those wings to have a greater surface area, which will allow a higher angle of attack when the plane needs to have a really short takeoff situation or also in landing. The slats are typically pilots are going to be deploying that when they're flying at lower speeds. Okay, so that's another condition. We also have your THS, which is your Trimmable Horizontal Stabilizer. That is fully moving. It's a fully moving horizontal tail surface. That also reduces the drag as the stabilizer surface, and then an elevator. As a stabilizer in service and the elevator are in alignment whenever that aircraft is in the trim mode. That trim there is, for reducing the drag. And then same thing with the spoilers. Remember I mentioned spoilers a bit ago. Those are also creating drag when it's needed. And the main thing here is it's intentionally reducing the lift. So that's usually before touchdown, so like right before touchdown. Those plates on the top surface of the wings can be extended upward into the airflow so that it's spoiling that. You also have speed brakes that are located on the wingtips. Speed brakes are created, again, those are for creating the drag. But this has to do mostly with speed. That's why they're called speed brakes, because they're reducing, they're slowing down the plane, so that's reducing the airspeed. I'm talking about the airspeed. They really don't affect the lift. Just think about those affecting airspeed. As a result of all of that, they're increasing the drag, as well as increasing the angle of approach during the landing phase. Okay, where are the speed brakes located? These are located on the bottom of the wing's trailing edges. That's where you'll find those. Okay, and what are the sources of power for the different, there's different obviously we have actuators to operate these control surfaces. So every single one of them have some mechanism. There's different kinds of actuators, and that's a whole lot of different things to talk about with actuators, because there's so many different kinds, especially with the increased technology, with computer software, etc., that you have, with the controllers, like with your PCUs, your power control units, etc., that are connected to the drive systems or your transmission systems that are related to the actuators. So anyway, that whole thing is just, can be built there to operate these control surfaces. So we have actuators, just as a general, brushstroke. You have your actuators, your servo control actuators that are running your primary controls as well as your secondary. Okay, so your ailerons, elevators, and your rudder. You have for your outboard ailerons, there are 2 servo controls, okay, running each of those. And then for your inboard ailerons, you have 1 servo control, and then you have also one servo control actuator and then 1 electrohydrostatic actuator. And I'll get into later how they're connected to the computers, which computers are in charge of which actuators, etc. It's a whole network of, connection. And your elevators, you have 1 and 1. So for each elevator, you have 1 servo control type of actuator and 1 electrohydrostatic actuator. Okay. And then when it comes to your flaps and slats, those are a different kind. Those are your rotary actuators. So it's just different design. But when you're talking about rotary actuators, those have to do with affecting the torque motion, okay, or rotary motion, right? Okay. So just kind of give me a brushstroke with the actuators, introducing that. And then I don't want to fail right now to mention a few review questions. So I'm going to go ahead and mention some right now so that you can write them in your notes. But let's go over some questions that you probably will see on the test. What flight control surface affects the roll of the aircraft? Is it the ailerons or the rudder? Okay, remember the rudder has to do with yaw control. So it has to be, the answer has to be ailerons, right? Okay, that's right. Ailerons have to do with the roll. Remember, kind of rolling down to the right or the left. Okay, next question. Which primary flight control counters the yaw? I just said it. All right, option 1, ailerons. Option 2, rudder. Okay, you're right. The answer is rudder. Has to do with the yaw balance, the lateral balance of the aircraft. All right, which primary flight control affects the tilting of the lift vector? Okay, tilting of the lift vector. Is it the ailerons or the elevators? All right, that's the ailerons. Okay, I mentioned about that. All right, next question. Which secondary flight control significantly affects the reduction of airspeed? Is it speed brakes or your spoilers? Okay, remember I said it's speed brakes. Speed has to do with airspeed. Okay, speed brakes. So that's the answer. Which secondary flight control significantly affects the lift of the aircraft? Is it speed brakes or spoilers? Yeah, you're right. It's spoilers. All right, the trimmable horizontal stabilizer increases drag. Is that true or false? That's false. All right, now let's go ahead and talk about your sources of power. Obviously, we talk about actuators, and in this particular case, we're talking about the hydraulic system. Okay, flight controls are run by the source of energy is the hydraulic system. And in the A350, if you haven't already gone through the hydraulic portion of the whole A350 jam fam, that you know, if you haven't gone through it, you don't know. But in the A320, we have 3 hydraulic systems. You have your green, yellow, and your blue hydraulic system. Well, the blue hydraulic system just, kind of falls off here. And when we're talking about the A350, we're only talking about 2 systems, okay, for your source of power. And that's going to be your green hydraulic system and then your yellow hydraulic system. Those are your 2 sources of power. All right, so just remember that for test purposes. Okay, let me go ahead and mention a little bit more about the actuators. There's a session on that, like I mentioned a bit ago, but I just want you to understand, or to just get you a little bit thinking of your primary computers, because you have a primary and secondary. If you've taken an A320 Gen Fam, some of the terminology is a little bit confusing, because there may be a reference to your SECs, okay, your SECs, as your short for your spoiler elevator computers, or your secondary, which is kind of funny because your elevators are actually part of the primary controls, your primary flight controls, and not secondary flight control systems. So again, a little bit confusing, but just understand when it comes to the A350, they are identifying the computers by name. So in this particular case, when we talk about computers and the ailerons, or any of these flight control surfaces, along with their actuators and being connected to XYZ computers, we're talking about your prim, okay, your PRIM. Okay, that would be then a number 1, 2, okay, or 3. And then you also have your SEC computers, SEC, which can be, again, 1 or 2 or 3. And again, those pairings that are there, because they run in pairs, because in case one computer fails, there's always that second one there. So just kind of think of that, just of the nomenclature of prims and SECs, okay? PRIM and SEC when it comes to being tied to the actuators, which are connected obviously to the control surfaces. Okay, I hope this gives you a good feel anyway for what the actual control surfaces are, where are they located on the airplane, what they do, describing what their functions are, and understanding that each of these has a drive system, or I'm talking about actuation system, whether it's having a drive system with a power transmission system or not, and you just simply have the actuators. And again, there's different kinds of actuators, but for this particular topic, we're talking about in general your servo controls in certain modes, and then we have rotary actuators when it comes to your flap and your slat control systems. All right, if you have any questions about any of the material for this particular session, please do not hesitate to email us or call us, and we certainly will do our best to help you with all of that. All right, well, thank you for joining this, and if you want to make sure you take notes, make sure you write these down in your handout, what we've covered in this session. We are on now to session 4 on actuators for the Airbus A350, part of the flight controls topic. On actuators, we're going to be going over the different ones regarding the control surfaces and the movement of them. As far as the actuators, they're operated 2 different ways, hydraulically and electronically, also electrically. So it's a combination because we have computer systems, right? We have computers. The hydraulic power that is used with flight controls, that are moving the actuators, are coming from the 2 hydraulic systems that we have on the A350. Now, be aware that we do have an auxiliary hydraulic system, which we'll get into if you haven't already taken it, the hydraulic power section or topic on the Airbus A350. But the 2 hydraulic systems that we have are green and yellow. So those are the sources of power. Like in anything that you're doing, you want to make sure that you're safe if you're doing installations. Your actuator safety. Make sure that you disconnect the hydraulic lines that are going from the actuators, because you want to make sure there's no pressurization in those hydraulic lines when you're working on them. So make sure that you disconnect those. Make sure you depressurize the system, as well as the reservoir for that. All right, and the backup control module, there's some computers here regarding the actuators. They're actually connected to the actuators, but we have a backup control module, as well as a backup power supply, just in case there's electrical failure, so that way the actuators can still run. All right, remember the pairs of computers when I talked about that with control surfaces. You have a Prim1, Sec1, Prim2, Sec2, Prim3, Sec3, right? And those are supplying the power, or giving signals, information, data, whatever commands, to the intermediary components. For example, you've got your PCUs and any other any transmission system to get over to the actuators so they can operate the control surfaces. So we have a backup control module and a backup power supply in case there's a failure of the computers. There's also a flight control backup control module. The backup control module, that I just mentioned, it's going to only operate the servo actuators and not the EHAs. Your EHA being your hydrostatic actuators, and also your electric backup hydraulic actuators. Those are not going to be run by that backup control module. There's another module that does that. That's the EM, your electronic module. Okay, and that the backup control module, like I said before, just if you had a total loss of all the computers, that's going to be the one that takes over. Okay. All right, so just wanted to give you first an introduction to power supplies that are there before we get really into the actuators themselves. All right, so let's go ahead and talk about the types of, just a little bit on types of actuators. There are different kinds of actuators that are used in different industries. In particular, of course, we're talking about aviation. So here in this particular case, we have your conventional servo control actuators. We also have another kind, which are they're electric. So you have an electric situation, is electrohydrostatic actuators, and then there's also the kinds that are going to be running the flaps and the slat systems, and those are going to be the rotary style. Okay, they're geared rotary actuators, but that's what you have for those. And there's two sides to the actuators themselves. You have one hydraulic side and then one electronic side. Each of them has a remote module that changes the signals from the digital to analog or discrete signals and vice versa. Because remember, the remote modules are there to be a translator. Okay, it's like you speaking one language and you're trying to communicate to another person who speaks a different language, and you have an interpreter that you're using, that other party's using as well, so that you two can communicate. That's just the same thing here when we talk about these modules, and they are connected to the actuators and of course to the computers. And with here you've got the hydraulic and electronic sides of these actuators. And within these, you also have two channels. One is for monitoring, and one is for communicating. So it's giving command orders, to get over to the actuators that are going to move the control surfaces. All right. Now let's talk a little bit about the electric hydrostatic actuators. Anything that's electrical. These become active when there's hydraulic or an electric failure. Okay. And the power is supplied by the computers that's sending the signals to the module. Okay, we're talking about the remote control circuit breaker that goes to the EHAs and your EBHAs, okay, your electronic backup hydraulic actuator. Power is also supplied through the power lines that go directly from the computers, and they're supplying a 60 volt DC. All right, so you know about that. And then the spoilers have the electrical backup hydraulic actuator. In particular, there's only the pair spoiler number 5. So that pair has a backup actuator, and that's that electrical backup hydraulic actuator. Otherwise, the other spoilers are using the conventional servo actuators. All right. Okay, and then let's just go a little bit more into that, just to give you a better idea. And then if you've seen these at all, just so you know, there's 14 spoilers, since I'm mentioning spoilers right now, and they are paired. And then we've got the computers that are in charge of moving certain control surfaces. So for example, and I'm going to go over some of this so that you just, again, you don't have to memorize obviously all of this stuff, but your elevator control, okay, you have one of each. So you have one conventional servo control, and then you have one electro-hydrostatic actuator that's in damping mode. Your active mode is, your conventional servo control is in active mode for the elevator. And then you have also your outboard aileron that's driven by 2 conventional servo controls. So elevator control is done by one servo control, and then you have the ailerons that are controlled by 2 conventional servo controls. Okay, those are going to be in active mode. And the other one that has 2 conventional servo controls is the rudder. Okay, so for rudder control, there are 2 servo controls there. Remember, what they're doing is just sharing the load. Okay, just so that there's it's dealing with the stresses of the material, okay, of the aircraft. Okay, and just to note, with the rudder, the hydraulic power is coming from the yellow hydraulic system. Okay, so that's for the rudder. Okay, all right, now you have inboard and outboard ailerons. Your inboard aileron is driven by only one conventional servo control, but it also has an EHA, which is your electro-hydrostatic actuator. Okay, and in those moments, and those pairs like that, your servo control is in active mode. All right. Now, as far as your computers, your Prim1, Sec1, the inboard aileron electro-hydrostatic actuator is connected to your Prim1 and Sec1. And I don't want to confuse it by mentioning all of the different combinations that are here. Actually, you can refer to a diagram and then also your handout, just to give you, some familiarity with the way that the pairs of computers are in charge of, sending commands to which actuators for X control surfaces. Okay. Now your spoiler control, those are driven by one actuator that's connected to one prim and one sec. Okay. Whether it's the parent, each of the three pairs. Okay, it could be one of the three pairs. And remember, I mentioned the spoiler 5 was something special. Okay, spoiler 5 pair. Those are actuated by the EBHA. Okay, the electrical backup hydraulic actuator. Okay, and that's an active mode. So that's just a special case, because the other 6 pairs are actuated by, remember I said, just regular servo controls. Now, what about trimmable horizontal stabilizer? Okay, that's part of, we're going to find this to be actually part of the primary flight control system. Again, don't get hung up by the terminology too much, because that changes depending on the model of aircraft. It also depends on the manufacturer. Boeing has a whole different terminology when it's describing the same functions that we have, of course, with the Airbus or any aircraft that's of this level of sophistication. So again, don't get hung up on that. Trimmable horizontal stabilizer control. Here you have 2 electrical motors that are responsible for the actuation of the THS. Okay, and one is connected to Prim 3 and Sec 3, and then you have another motor that's connected to Prim 1 and Sec 1. All right. That's pretty cool. And you can probably look at diagrams on different places. Maybe you have already. Of course, if you've been on aircraft, it's pretty standard as far as the location of your spoilers and your inboard ailerons, your outboard ailerons. But as far as what's controlling them, may be slightly different. Okay, it's just there's always 2 or 3 different ways to still get the same result, right? So, with here in the Airbus A350, we have this configuration. Okay, and remember what I said about the servo control actuators having 2 channels, because it has to have a channel for monitoring, which is going to be receiving feedback signals from the actuators, back to the computers. Okay, so there's 2 channels, just like we haven't had in other aircraft. That if you're taking other gen fams, it's the same functions, same features that we have with the computer software, or excuse me, the computers. Your one command channel and also one monitor channel. Okay, and they're just exchanging data from through the internal bus so that it can obviously have the servo function going. All right, the components that you have, these are line replaceable units, your RLUs. Is your flight control, remember flight control remote module that I said earlier? Those are for your servo controls. And then you have your EHSV. Okay, that's a solenoid valve. That's your electrohydrostatic solenoid valve. You also have a active damping solenoid valve, soft hard damping solenoid valve, and your transducers. All of those components of the servo controls are line replaceable units. All right, and then with the actuator, like I mentioned earlier, just briefly, I was saying that there's a hydraulic side and on the electronic side. And what can you find on the electronic side? Obviously electronics, right? Well, what would that be? Well, it's going to be your modules, right? These modules are computers, or little, I'll say little, but compared to other physically, as far as in dimension, they are computers, the way that they're functioning. So, those are all going to be on the electronic side of the flight control remote module. And of course, you have your hydraulic side where you have the hydraulic components. Okay, and there's rudimentary diagrams that you might see just to give you a bit of an orientation of the inputs and where they're going to, and then from there, where's the output going and what's the final result. Okay, obviously we're talking about control surfaces being moved. All right, and just keep in mind too that all of the computers are calculating constantly based on the ADARUs, all the air data information, attitude of the plane, etc. All this is coming from sensors that are going right into the computers, and those computers are already assigned, if you will, where they're going to be sending those signals, whether it's going to be for rudder control or to the ailerons, for that control. or the elevators, etc. Okay, for your pitch. So just keep in mind it's working very systematically and very deliberately with where it's going. All right, your electrohydrostatic actuators. It's an electronic module, right? And it also has the 2 channels, just like the FCRM, like the flight control remote module. So you have your command channel as well as your monitor, your monitoring channel. There's also another little unit, so I say little unit, but there's another unit that exists here with the EHAs that you don't have with the servo control actuators, and their flight control remote modules. This in particular is your power electronics unit. And this is just a part of the electronic module that is part of it. And what it's doing, why is it even there? Why a 3rd unit? Well, because it's having to convert AC power to DC power. And in particular, just so you know, some aircraft are not going to be dealing with 540. And if you're in, if some of you are maybe avionics people and have had some background in electrical engineering, you'll understand that there's usually on the plane you're talking about 28 volt DC and your 230, right? And some 110 AC. Here we're having to convert AC power to DC power, but it's interesting because usually we think about DC being a lower voltage, and yet in this case we're talking about 540 volts in DC direct current. So just to keep that in mind of what that's doing, and what now we're dealing with, a whole different configuration, because we have a much more sophisticated plane with the A350 than we do with, say, for example, with the A320. All right, so 230 volt AC to 540 volt DC, okay, to supply the electrical motor and also the drive solenoid, the direct drive solenoid. So that is what it's there for. All right, the motor, of course, is going to be driving a pump, right? The hydraulic pump, which is going to, create pressure so that it can power the actuator. And that's what we have here with that. There's 2 valves, or 2 solenoid valves with this, the active and damping mode, your active and damping direct drive solenoid valve, and then you have your hard soft damping solenoid valve. Those are 2 existing there. There's also another module. I know I said there's a 3rd and that's it. There is another module. It's actually mounted on the center line of the actuator itself, and that's your non-volatile memory. Okay, and what is it doing? Why is it even there? Okay, well, this is going to contain values and also the calibration points that are going to be used by the electronics, okay, module, the electronic module. It's also containing just basic vital information, if you will, of the actuator. That's your part number, functional item number, excuse me, and also the serial number of the actuator. So it's pretty cool, actually. It's a tracking. It's an amazing little machine to do all that, but that's what it does. Okay. Also, besides of course, you have reservoirs, so that you have hydraulic fluid moving and going where it needs to go to the actuators. But you also have an accumulator that's supplying fluid to the EHA. In this particular case, an accumulator is supplying the hydraulic fluid to the electrohydrostatic actuator. Okay, so it's compensating for the fluid volume variations and any leakage. So again, it's a backup, right? It's a backup reservoir, and that's what it's there for. The EHA, the actuator, is hydraulically connected to the servo control actuator hydraulic system. Okay, so it's all part of that, and it's just there to refill the EHA, and also for isolating from the entire hydraulic system. And there's different few different valves that you'll see is that there's a mode selector valve as well, and that's just for test purposes. And of course, transducers, if you're not familiar with electricity or the topic of electricity and all the different components regarding that, Your transducers are also hydraulic components, and that is going to be, transducer is just simply a component that uses pressure to measure, okay, to sense, and then it sends signals to, you know, where it needs to go, and it gets translated after that. So, but that's what transducers are. Those are part of here with the, when I'm talking about the EHA operation. Okay, it's basically just sending the signals back to the electronics module. Okay, all right, so I just want to give you an idea a lot more on the hydrostatic actuators, and please don't get bogged down by all the acronyms regarding everything in the Gen Film. It's really crazy to think about how many acronyms there are, and there's lists everywhere. I'm going to try my best to keep things on tests, you know, not abbreviated, not with acronyms, unless I reference it in a handout and you have it available to you. But anyway, I'll try my best to keep everything spelled out so you don't have any questions whatsoever. All right, remember I mentioned that special pair, spoiler number 5 pair, because that's the only pair of spoilers that's being run by the electrical backup hydraulic actuator. Okay, that's different from the EHA. Just to differentiate, we have an EBHA, which I'm talking about right now, your electrical backup hydraulic actuator that runs only the pair of spoilers number 5, and then you have the backup, I should say backup, but you do have the electrohydrostatic actuators. Okay, so, but the other spoilers are an active motor running off the conventional servo controls. Okay. And just, you know, a little bit on the spoiler number 5, or the pairs spoiler number 5. It's using this servo control actuator. It is a servo control actuator. It's just kind of a mixture of a hydraulic actuator, because you have electrohydrostatic as well as it being a servo actuator, a servo control actuator, and they're just put together essentially in one place as far as architecturally. Okay, and it also has a power electronic unit to it. Okay, now if you needed to test this particular actuator, there's a visual indicator that you can use, and you're testing all of this on the ground. If you have a loss of hydraulic pressure, then that voltage, that power is going to be changed to 540 VDC. It's kind of like, I was just thinking about other aircraft. If you take a Gen Fam A320 or Boeing 737, you know, whatever, usually when we have things running, they're running on 110 volt AC, right? And then when there's an emergency, then it's going to be utilizing the 28 volt DC, okay, to run things. And here it's doing the same thing with changing alternating current to, direct current, only our direct current is not 28 VC. In 28, we're jumping to 540 to supply, power for different areas, different components. Okay. All right. So that's, just so you know, that's what is involved with the electrical backup hydraulic actuator is the maintenance on it. It can be set to a maintenance mode. There is a key receptacle, and that's used for selecting, the maintenance mode, so that you're aware of that. All right, I think it's time for some test questions. I don't want to forget that. All right, here's a true-false question or statement. Each control surface device can have a combination of the different types of actuators. Is that true or false? That is true. Next question. Which electrohydrostatic actuator, which electrohydrostatic actuators are not controlled by the PRIM2 and SEC2? Okay, is it the actuators for the inboard ailerons or the actuators for the rudder? That's going to be the actuators for the inboard ailerons. Those are not controlled by PRIM2 and SEC2. And there's a diagram that shows all that that we have for you. Each of the elevators is actuated by which two actuators? Is it two servo controls or one servo control and one electrohydrostatic actuator? The answer is the second answer. Okay, so when it comes to elevators, you have the two types in combination. You have one servo control and one electrohydrostatic actuator. What two sides do the actuators have? Is it pneumatic and hydraulic or hydraulic and electronic? The last one, right? Hydraulic and electronic. What is the function of the electrohydraulic servo valve? Okay, is it to provide hydraulic fluid to the chambers of the actuators or to provide electrical power to the electrohydrostatic valves? Okay, the answer is the first answer. Okay, which module is installed with the power electronics unit? Is it the first answer, which is your FCRM, that's your flight control remote module, or is it the EM, your electronic module? And you are right, it's the last answer. All right, let's go ahead and go back to our subject here. All right, let's go on to the computers that are in charge of the actuators. Okay, there's three different groups here. All right, this is all kind of probably a little bit will overlap when I talk about the primary flight control system, and you know, we're talking about the computers there, the commands and monitoring functions, etc. But you know, you're going to get a taste of it right now. All right, so let's go ahead and go into this. With what we have here, and by the way, there's two different kinds of lines that are running. You have the MIL 1553, which MIL, by the way, says for military. This was an old line that has been used in the military for many, many years. Obviously, has been reliable. Otherwise, it wouldn't be in the A350. So it's part of the lines of communication between prim and set computers and the actuators. Okay, so between the computers and the actuators, you have to have a network, and that network is the MIL 1553, okay, along with couplers. And when we talk about between computers, okay, so we have communication between computers, we're talking about the ARIC 429. Otherwise, it's the MIL 1553 when we talk about that. All right, digital network, you've got your COM and your MON buses, okay, your buses for commands, signals, and then your MON buses for monitoring. So the computers are doing what? Okay, they're sending those deflection orders. This is all based on aircraft data, okay, that they're getting from different sensors. The computers are getting all that, sending those deflection orders, because there's certain deflection angles, rates for the operations of the flaps and slats, for example, depending on, you know, any given point in time in the flight phase, the attitude of the aircraft, you know, all the different variables that exist at one point in time, right? Correct? So that's what it's doing. It's sending those orders to the actuators, and then it's monitoring that data that's received back from the actuators. And as far as signals goes, if you're not familiar with signals engineering, that's a whole different field, which is pretty complex and excitingly fun. But that those analog and discrete signals are coming from the actuators and going back into, right, we have to have a translator, an interpreter, like I said before, right, if you had to communicate with some other person. So there has to be a go-between. And those signals are going into the modules and then going back to the computer. And the computer is gathering that data again, along constantly with the input from the sensors. Okay, so pretty interesting setup. Okay. Now you have a local servo loop, and that is done on each actuator, and it's done with the modules, okay, whether it's your FCRM, your flight control remote module, or your other one, your electronic module. Okay, and those are controlling the valves on the actuators so that it can get that right deflection. Okay, remember I said how important it is to have the right deflection rate as well as the angles. This is the information that the computers are getting, so that they can figure out or give those commands and control those valves. Your couplers are also components of the actuators. They're not as active as the other components, but they are there. They don't have any software. They're just completely like there physically installed in the pressurized areas. You can easily replace them. They're accessible is what I mean by that, and I'm sure they're easy to actually install or do installation. Those are easily accessible to get to. Okay. All right. Okay. So let's go ahead and go get bearings here. That's what you have with that. Now, and just keep that in mind with the wiring network, because when you start working in the A350, well, it might be a slightly different configuration, and it will be. And I'm talking about in comparison with the A320. When we get to hydraulics, I'm going to get into more detail on the differences in the way that's set up. It serves the same function. It's just configured differently. Okay, it has to kind of make do as far as space and regarding the architecture and the design engineering of the plane itself. So that's why. All right, let's go ahead and go to a little bit on the power supply. I know I probably mentioned a little bit earlier about it, but your power supply for the modules, okay, those are your interpreters. Okay, those are the power supply is sent through the circuit breakers. Okay, there's one remote control circuit breaker that's activated by signals from the computers, whatever pair it is. Okay, now remember I said about testing. You can test the actuators. When you're on the ground, you can test and you can actually operate the actuators. Of course, in order to do that, you need to pressurize something. Otherwise, right, you can't do the test. So you do need to have at least one hydraulic system or pressurized and one engine running. Make sure you do follow procedures for safety purposes. Okay, and then just decide which hydraulic system you're going to be operating. Okay, and then also you want to make sure that the low oil pressure switch is not low. Just some things to check. Okay. All right. Just a little bit on the hydraulic system interface, or just so you understand a little bit about the hydraulic systems, and I'm talking about the green and the yellow, and they're identical. I mean, as far as, and I don't get too much on hydraulics. I just wanted to share a little bit that there's two systems, the green and the yellow, that the flight controls rely on. Obviously, all the components involved in the whole flight controls, and they're not the same capacity, and there's a reason for that. Okay, so just they're having designated functions, which is tied to certain control surfaces. Okay, and that's why. But I just wanted to mention that briefly to you. Okay. All right, that covers actuators, and just I hope you learned something about the Airbus A350 as far as the types of actuators that exist here, and we also have, like I mentioned, there's geared rotary actuators that operate similarly. Those actually have power control units associated with that, and then of course you have servo control actuators, and then those that have an electrical or electronic component to it, and those are your EHAs and your EBHAs. Okay. All right. Make sure you refer back to your handouts and review the questions. Make sure you did write down the answers that, when we were going over it. If you have any questions about anything, or you missed it, maybe you didn't understand something, misheard something, whatever, and want clarification, please make sure that you email us or give us a call, and we will do our best to provide that information to you.